It makes me a great pleasure to introduce Matt, Matt Mason. Let's see, I'm going to run through the highlights of his career. So he graduated from MIT's AI lab in 1982, and then he did some other stuff. So.
That's it. No, you left out before.
No. But no, it's a product of MIT also, so we should feel proud of that. But after that, he went to CMU, where in 1982, where you started, right? 83?
82, yeah,
82.
1982.
Yeah. Was very close to the origin, the beginnings of the Robotics Institute at CMU. So in some way, Matt has had a very strong influence in its trajectory as well as its culture, which is the thing that if you've been there is something that you can clearly see, including 10 years as director. Matt works in robotic manipulation, or manipulation in general, it doesn't need to be robotic. He has received many important awards from IEEE, Technical Field Award. Okay, sorry.
That's enough.
There's another one. There's another one. Okay. This is why you need to bring cheat notes to your.
I got the
IEEE Research and Automation Pioneer Award. There you go. And more recently, in 2014, as we see a trend in many of these talks, he decided again that that wasn't enough. So he decided to join a startup company, Berkshire Grey, which spent about 5 or 6 years in stealth mode, while almost everyone knew what they were working on, but they didn't want to say.
You just thought you knew.
Exactly.
And you turned out to be right.
A company that works, local company, based in Boston, that works in robotic material handling. And I'm hoping that you will talk somewhere in between that connection, or maybe not.
No, I'll talk a little bit about it.
Anyway, it's an honor to have you here. Thank you very much for coming.
Thanks.
Please.
Thank you. Thank you for the generous introduction. It's great to have you all here. These talks are great opportunities because not only do I like to hear myself talk, but the pressure to think, to say something worthy of your interest is really awesome. And so I've been thinking about what I'm going to say here for weeks, and who knows? We'll see how it goes. The question, it occurred to me as I was going through this process that the question I was really struggling with for this talk is the question, how do we learn about manipulation? So in robotics, I think it's a lot of times assumed that the question is, how do we build robots? You know, what cool technology can we build and transition into industry or whatever? But here it ends up being about how do we learn about manipulation? And there are many ways, but by observation, and specifically you can look at humans, you can look at robots, you can look at telerobots. So I'm going to go back over this a little more carefully later. And you can look at the robot building process. And so building robots turns out to be intimately connected with how do you learn about manipulation, because it's a really good way to learn, and also because the more you learn, the better a job you can do with building them. So they're intimately connected, but not really the same problem. But let's see. So, oops, somehow I just skipped right past that. So that's a thread that's running through the whole thing, you might say. I have this outline which kind of describes the sequence I'm planning to talk in. And the first thing actually gets back to, we were talking about, when I was here in the AI lab, now known as CSAIL, or now known as part of CSAIL. And basically how I got started, specifically on being interested in the modeling the physics of grasping. And then I'm going to talk a little bit about how did I get interested, how did I get involved, how did I get traction in dynamic models of manipulation, and then talk about the relation of academia to industry, including what looks suspiciously like a plug for Berkshire Grey. My finger seems to be bouncing on this button. That's interesting. OK, so how did I first get traction in physics-based manipulation? Let me tell you where things were in 1976, or the state of the art in 76. Actually, I'm going to go back all the way to 61. So this is Heinrich Ernst. And I think 5 minutes ago, we might have walked right past the room where this project was happening. This is a teleoperated arm. Now, that's something you don't see these days very often in videos about robotics. It's a video of him smoking a pipe, drinking coffee, reading a newspaper, okay? There's a point to it, right? He's communicating to us that, look, you know, we can relax, we can be lazy and let the machines do the work. So this is, in some sense, the real point. And this is like the first PhD in robotics. So, you know, maybe that point needs to be made. His supervisors were Minsky, and I forget who. Anyway, his thesis, obviously you can find his thesis in the MIT archive. It's interesting. This is a little bit later. This is the copy demo. So this was going on when I was an undergrad here. I got involved kind of towards the tail end of this. Now, these people are all moving blocks around. And so the blocks world turns out to be a task domain that a lot of different groups converged on. Take a bunch of toy blocks and see if you can move them around. No real commercial application, I guess, but nonetheless an interesting application and a task domain. So, you know, if you can solve this task domain, if you can solve blocks world manipulation, surely you will have learned something useful more generally. This is what was going on at Stanford. This is the instant insanity demonstration. This guy, Richard Paul, did a PhD thesis on it. And more blocks world stuff. My finger keeps, oh, I know what the problem is. No, I don't. That's just a photo. It's not going to start moving, OK? Don't hold your breath. That was at Edinburgh. Here's a project. Well, this is really the most impressive of all of them. This is Shaky the Robot, which I imagine a lot of you know. It was automatically deriving a sequence of actions in a very principled way from statements of goals and world models and axioms that describe the actions that it can do. But it's in blocks world too. It just has really, really big blocks, and it doesn't have a gripper. So in fact, a lot of people forget that it was a mobile manipulator. In fact, not too long ago, I ran into one of the guys that did this paper, and I said to him, like, hey, you know, a lot of people haven't noticed that Shaky was a manipulator. And he said, yeah, I didn't have a manipulator. So, drives me a little crazy, and in Japan too. So this is at the electrotechnical lab. So, you know, really it was an amazing convergence of opinion in these groups that the blocks world would be an interesting place to work. And a lot of stuff going on. Now, well, actually not a lot of stuff, you know, compared to now. I've probably shown you maybe even half of the groups that were doing this kind of stuff. And a lot of it was focused more on vision, really, than on manipulation. I think people were more excited. Finger bounce is just going to drive me crazy, this whole talk. When I got here, this is what we had in the lab. This was called the MIT ARM. It was designed by the same guy that built the Stanford arms that we were looking at a second ago, Victor Scheinman. It's got this nice gripper, and you know, we were using it to do blocks world stuff. Okay, and now, so here's where the story begins. Like, I'm a new grad student. I have no idea really what research even is, okay? I can remember going into the physics reading room thinking, oh, okay, I'm supposed to go read journals and pull out a journal and it's like, I cannot make any sense out of this at all, right? Or go to a talk in the AI lab, maybe somebody's talking about linguistics. You know, and I just don't have, you know, or you can go in and stare at your monitor and think, okay, I'm doing research now, I'm writing code, you know, nothing's happening. So how do you get traction, right? How do you first, you know, what I think this means is, how do you first learn something new? Not, you know, not just new to you, but new to anybody, right? How does that first happen? And for me, it was with this arm, I decided I would try to move a queen around on a chessboard, okay? And so we just pick up the queen and put it down and pick it up and put it down and pick it up and put it down, pick it up and put it down. And oddly, after about 5 or 6 moves, the queen would fall over, okay? Seems simple enough. Why should it happen? If it's gonna happen, why shouldn't it happen on the first move? It never happened on the first move. It was always after several moves, okay? Now what I think was happening was this. In time, in real time, the process seems stable. But if you look at it as an iterative process, it wasn't. So let's say there's initial error where the queen is a little bit to the left of where it's supposed to be. When the gripper squeezed it, it would tilt it a little bit, and then it would move it somewhere else and place it down and let go of it. And when it lets go of it, there's a little bit of potential energy in that tilt, and it would rock back and forth, or maybe it would scoot a little bit when it, so I made a video. I did an experiment. You can see there's a recent experiment because, see, it says BG up there. So it started at this line, and I'm going to consistently nudge it to the right, and you can see that perversely, it's moving to the left. And it may not be quite obvious to you yet, but pretty soon it actually covers up that line. It's not, you know, it's not deterministic. You know, it doesn't always move to the left, but it tends to. And I tried a few different scenarios, and this happens pretty often. You can take a pop bottle and tilt it on it, put it on a table and tilt it and let go, and it'll slide. So maybe that explains what went on. Now there's an interesting thing you can do. Let's suppose that instead of grasping it at the top, you decide you're going to grasp it at the bottom. Oops, finger bounce. Damn, I got to push that again. No problem, right? It's not going to go back to the left. You know, it's this mechanically robust thing that happens. With pushing, you're not putting energy into the system that could end up biting you. Instead, the energy is getting sucked out instantly by the friction, okay? So it turns out that squeezing things at the bottom can be sometimes mechanically more robust. Okay, so now remember, I'm just a newbie. I don't know what's going on. This is interesting. I don't know. Is it important? I don't know. Here's another thing that I did. We were all very excited by what the people at SRI had did with Shaky the robot. So I'm thinking, okay, I'm going to do some formal stuff. I'm going to like make up some axioms, and I'm going to take this program. I'm not going to try and derive the program from the goals. That's too complicated. I just want to prove that this program works. So, you know, what could be easier, right? This is like the simplest blocks world program. Squeeze the block, move it to where you want it, and unsqueeze it, okay? So prove that this program works. Now, I knew that I wanted to worry a little bit about error, maybe because of that thing with the queen. So let's say we're not going to assume that the position of the object is perfectly known. And in that case, the problem is this is where I got stuck, right? Assuming this is the initial condition and you close the gripper, how can you provably end up in that state? You know, what are the axioms to write? What's the reasoning process? And I could not solve that. Years later, I realized that you can set up that you can choose a coefficient of friction such that that actually will not work. So in retrospect, it's really good that I couldn't prove that it would work. This is the one that actually caught my attention. This is what I worked on for the next like 30 or 40 years, okay? But most notably, and this is what I did for my PhD thesis, is show that even if this thing is cocked a little bit, when you squeeze it between these two plates, it'll straighten out and be centered, okay? And at the end of my PhD, I actually did have a proof of that based on Newtonian mechanics, based on you need to know where the center of friction is, at least within some bounds. You need to know the coefficients of friction, at least within some bounds. There's some assumptions that the friction is uniform in space. And subject to a bunch of assumptions like that, you can actually prove that that works. Now, still, think back, to when I was a newbie, right? Is this really a good problem to work on? Is this really going to get us anywhere? Nobody seems to be talking about it. And then I heard this video. It's amazing.
The third segment demonstrates the mounting of a hinge using two arms. The arms cooperate, but in one of the simplest ways. That is, only one arm moves at a time. The blue arm first pushes and then centers to locate the hinge.
He said the blue arm first pushes and then centers the hinge. So now, to me, that was the world, right? That's the evidence that it actually matters. Because, Ernst's program did this. It squeezed the block got centered and aligned, I guess. I don't remember it not being aligned, okay? Did Ernst know that? Did he use that to do the planning? Does it really matter? Seems like it didn't. The instant insanity guys, they weren't worrying about it. Did it matter? It seems like it didn't. Maybe it's one of those things that's just kind of an interesting quirk of nature that helps us out and we're all happy and everything, but does it really matter? And could you get a PhD for spending a couple of years studying it? Here's the evidence that you really could, that it might be worthwhile. That finger bounce is amazing. It's so consistent. I swear, I never had that problem with this computer. It's something about this audience that's doing it. You all know about cytons? Oh, this is a stupid question, isn't it? How many of you know about cytons? There's a theory that I learned at MIT. It's interesting that it doesn't get around very much, but the idea is that demos work until the audience shows up and looks at it. And what is the cause of that effect? It's because visitors emit cytons from their eyes, which interfere with your experiments. And the bigger shots they are and the more bigger wallets they have, of course, the more cytons they emit. Anyway, this was AI lab culture, okay, back in the day. So, this is a little goofy, but you can look at this as a kind of experimental thing, right? Ernst didn't think it mattered, I guess. I would guess the people who did the instant insanity, the people who did the copy demo, none of them thought it mattered. But I did the unstable queen, and it seemed like it mattered there. The hinge assembly, that was Bob Bowles, by the way, doing the narration, the same guy that invented Ransack. Bob Bowles thought it mattered for the hinge assembly. Russ Taylor, he had a PhD thesis where he squeezed a lid and a box together like this 2 times to get them nicely aligned with each other, okay? So, so there's a kind of experimental evidence. Now this gets us to the question that I first asked, which is, that finger bounce again, I'll be damned. Okay, yeah, forget you saw that. What do we learn from? Well, you can learn from watching humans, for sure. You can learn from watching a robot. Okay, there's a robot. Telerobotics is a nice way to learn stuff, right? Because one thing is that if you want to learn from a human, there are limits. You're not allowed to take them apart, okay? But you can take a telerobot apart, right? You can put a scope on the signals, and you can play games. You can put fuzz on the picture that the guy's getting in order to see how much sensor noise he can stand. And so there's a lot of things you can do with telerobotics that's very nice that way. But all of these are, I'll call it, all of these are manipulation systems where, let's say, intermittently you can push some desired behaviors through, and then immediately you can see whether you're getting those behaviors out of the system. Now there's a fourth system. I just need to do that. I need to learn a new. Somebody, Jean Vertut was the guy's name, a French guy who worked in Telerobotics, and he said, you know, if you have a person that programs a computer, you can look at that as being remote in space, like Telerobotics, and time, okay? And so let's say we give the desired behaviors to this system, and then there's a robot in this system, but then there's a wrapper. So this is like, is this term still current in software engineering? If you have a function and you don't like the interface, you wrap another function around it, right, to change the interface. So here you have an autonomous robot which has some scope, some capabilities, right? And what you want is a larger, let's say, scope or different scope, set of capabilities, and the wrapper is this programmer, right, who's going to write some code to make up the difference. And then, when you're actually running the behaviors, the programmer's out of the picture. I would have had him smoking a pipe and drinking coffee like Ernst, but my artistic skills aren't up to it. So he's just taking a nap, okay? While the robot does all the work. So that's, you know, Spacetime Telerobot, I'm calling it. I don't know if others have come up with a better name for it. No bounce. So, okay, well, I'm coming back to that. At the same time, so let's see, there's an interesting thing happened. I was trying to write a book. I thought, I'm going to use a book to organize my life, organize my career. I did this work on grasping that used quasi-static models. How do we organize all of manipulation? And it occurred to me then that you could view earlier work, let's say on path planning, collision avoidance, by people like Tomás Lozano Pérez, who developed the configuration space technique, and many others. You could view that as kinematic manipulation. The model that's in your head when you're developing an autonomous robot that's just doing path planning and collision avoidance is entirely kinematic, right? Your model is that it's either attached, firmly attached to the gripper, or firmly attached to the ground. And you're avoiding collisions because those would be kinematic constraints that you don't want to violate. So you could call that kinematic manipulation. Now, if you want to worry about the stability of a grasp, or when you're stacking up blocks, you want to worry about the stability of an assembly, you could call that static manipulation, because you need to make sure that you have a static equilibrium in those cases. The kind of stuff that I have been doing was quasi-static manipulation, and then that suggests, so here you have a kind of progression. There are many different ways of looking at manipulation. I'm not saying this is the way to look at manipulation, but it's a way to classify skills in terms of these mechanical models. Now, it's a little tricky because every manipulator, you can't build any manipulator at all without having some dynamic models, right? So think in terms of the wrapper, the space-time Telerobot. If you have a robot that can control, that can follow a specified trajectory, and then ask yourself, what model does the programmer need in order to add these other capabilities to that? Okay, that's, I think, the right way to look at this. So it kind of stipulates that programmers have these models in their head, and I've tried, and I cannot figure out a compelling argument that human beings have models like this in their heads. But that's okay. We don't have to prove that. We're all engineers. We're all from MIT. We love models, right? Engineering models, classical mechanics models, I think. I'm not sure I'm seeing universal agreement with this concept. Okay, what can we do with dynamic manipulation? So, for me, I've been doing this, static and kinematic was kind of looking back, and the question is, what can we do with dynamic manipulation? Dynamic manipulation turns out to be interesting for a few reasons. First off, it's hard. It's really hard. I mean, if you're looking at it especially from a planning point of view, okay, I had actually, it's hard to believe, but I've actually become kind of comfortable with a 6-dimensional state space, okay? The configuration of a rigid body or of a gripper in space would be, X, Y, Z, yaw, pitch, roll, 6 degrees of freedom. Actually, let me take that back. I wasn't comfortable with that at all. We almost always did planar problems. I'm really fairly comfortable with 3-dimensional state spaces, okay? X, Y, theta. But when you throw in dynamics, now you have twice as many state variables, right? Because now momentum counts. So you need x dot, y dot, and theta dot as well. But dynamic manipulation is also powerful for the same reason, okay? Because if you're not doing dynamic manipulation, if you're doing quasi-static or whatever, okay, the only action you get is when there's contact, and that means the object's workspace can't be significantly greater than the manipulator's workspace. Whereas if you have dynamics, you can use your limited workspace to pump up some momentum, right? And then that momentum is integrated to give you motion outside of the robot's workspace. So, okay, very, very fancy way of saying now we can throw things, but that's, it's good stuff, right? And I couldn't resist, okay? It is beautiful. I don't know why. I think, if you ask why, I think it's because that evolution selected us to favor people who can throw well, perhaps because it's good in hunting or in warfare, or just the other day it occurred to me, it might be, one of the great things about being a human is that we have these dogs that seem to like us and hang out, and they're really great companions and everything, and they love to play fetch. And I can't help wondering if maybe they and we are evolutionarily programmed to play fetch together. So it could be that. In any case, the people that are good at this, we give them millions of dollars, and you should go online and do a search on Drew Storen, D-R-E-W-S-T-O-R-E-N. We don't have time to look at all this kind of stuff today, but there's a 1,000 frames per second video of Drew Storen's baseball pitch, and it is amazing. And if you do the math, in that baseball pitch, over the acceleration phase of the baseball, that baseball is getting an acceleration of about 140 gravities. Okay, it's astonishing. Now that's a professional. I am going to show you a video of what I'll just say ordinary people do. Maybe they're not ordinary. I think they also are highly skilled and spent a lifetime and so much going on here, it's really hard to fathom. Obviously, a lot of throwing, a lot more throwing probably than you had expected. And some very interesting kind of throwing too, like whipping that dough around to stretch it out, right, is interesting. And this video goes on for like another 5 minutes with many other equally fascinating things. So for that, you should Google awesome skills or awesome cooking skills, I think. And you will find this video and many others like it. Great stuff. But this is not what actually inspired me. So the thing that I learned from when I was first doing dynamic manipulation was this human being, Michael Cass. Some of you would know Michael. He was a vision researcher and a computer graphics researcher, and then he went to Apple, and I don't know where he is now. This is world-class juggling, okay? This is not easy stuff by any means. But that's the money move right there. Well, not money, he was an amateur, but. And if there isn't really a national championship of juggling, but the International Juggling Association has an annual convention, and they give a prize. And he won the prize one year, basically because he could juggle with his feet better than anybody else. So being able to toss a club up with your foot is fairly common because you got like, 6 people throwing 30 clubs around, and then you drop one, what do? You don't want to stop and restart. Instead, the whole group kind of moves rigidly and scoots around until one of you can get your foot under the club, and then the whole time they're juggling this pattern, and then when the hole in the pattern comes around, they kick the club back up into that hole and keep juggling. That's pretty amazing. But this was, he was the only one that was really working it into his, anyway, okay, so juggling. He's very good. This is a sort of strobe, tracing from the video onto acetate. And then I built a model of Michael Cass, okay? Did I mention that I like planar state spaces? So this is the planar Michael Cass. There's no power, there's no electricity, there's only gravity power. So I was trying to figure out how can I be confident that I'm getting a very constant and repeatable torque for this system. And with some help from Ben Brown, who has, many of you have seen his work because he worked on some of the early Raybert hoppers, some of the early Boston Dynamics stuff. Anyway, he helped me with this. So this wire goes around that pulley. There's a counterweight there to balance the leg and the club. And there's some pegboard here, and you can move the pegs around between those pegboards to vary the grasp. And then the question is, can you design a grasp that will do a clean release of this club? So what you want is that you're going to have, during the acceleration phase, there's going to be no slip. It's going to stay in contact with the club. And then, you can't really see it, but there's a cable going the opposite direction about that pulley. And when that cable goes taut, suddenly the leg decelerates. Okay, and now what you want is a very clean release with no slip, cleanly letting go at both fingers. And if you do that, you get a nice throw, but that constrains the design of the grasp. So the game here was to figure out exactly where you could put those fingers and get the right thing to happen. And that's another strobe. Okay, anyway. Not a lot of time to look at this. There's a paper out there which has like scatter plots, and it did give you a nice, reliable throw. And we went on to do some work that I'm also not going to show you. But Kevin Lynch did his PhD thesis in this area and did some very nice work that some of you, I know, are familiar with. But that's where it started. Okay, this is how I first got traction. This is how... this is kind of the first time I felt like I learned something new about dynamic manipulation. Now, I did not appreciate at that time the applications of it, the significance of it. That came quite a bit late, quite a long time later. So let's think about what it means to throw something. Usually, the idea that you throw something means that you let go of it. So you give it some momentum, and then you release. And so it's flying out there on its own. But suppose we play with that a little bit. So suppose that you don't entirely let go. Suppose that you have constrained all of its freedoms but one. So one thing is that humans, we seem to be really good at modulating our contact force here so that I can turn that into a pin joint. It's amazing that you can do that, because you would think if it's loose enough to slip, it would do that, which would be bad. But you can hit this middle ground where you have pretty good pivoting without the translational slip. And so now you can view this as an unactuated link attached to my fingers, okay? And so maybe that is a kind of throwing, because the way I'm controlling that last freedom is by using its momentum, right? I'm pumping some momentum in and letting the momentum integrate to give me some motion. And you could do some other things too, which I'm not going to try with my phone. But you should try with your phones. because there's 6 possible degrees of freedom, how many different partial constraints are there? This actually ends up being an interesting problem, but not for today. Partial closure grasping is something that's kind of been out there. I know Antonio Beakey has published something on it. I'm not sure. Do you know, has anybody else published on partial closure grasps? Anyway, so let's say we have a partial closure grasp, and then we're going to use dynamic manipulation to control the other freedom. And then the question is, what can you do with it? Now, I'm kind of going to take a jump here to show you this, okay? Now, this is work that was a collaboration with Alberto and Nikhil Shavandafel. And this, I think, is like, this is the killer app of dynamic manipulation. Maybe throwing baseballs is the killer app of dynamic manipulation. But anyway, this is pretty good. This is, so this is a very simple gripper. It's only got 3 fingers. And those fingers are attached to a single motor. So when that motor runs, the fingers only do this or that, or they're springs so that if they contact something, they can conform to the shape of the something, okay? But they can't move independently. And what's more, every finger has a single degree of freedom. So it's 1 motor, it's 3 freedoms, okay? It's a relatively simple gripper. Now, if you consult the literature, if you kind of survey the literature on how do you control an object in the grasp of the hand, the most prominent idea, which people sometimes call a dexterous hand or dexterous grasping, is to have 3 point contacts, okay, that are not collinear. And in which case you now, if you could move those points, you can control the attitude of the object. And so if I can control the motion of those 3 point contacts, each of them in X, Y, and Z, this object will be controllable, okay? And there was a lot of very interesting work that went on along those lines and which relaxed some of the assumptions. There's actually a great body of work there that's really interesting. But notice that it's a rather complicated thing, right? You've got to have 3 fingers. Each finger has to have 3 controllable freedoms. So you end up with hands with at least 9 motors. And what's more, the control of it's tricky, and honestly, most of the demos you see don't work very well. Maybe there's people in the room that I'm accidentally dissing with that statement. But I know if you go back, for example, to some of the dexterous grippers that were built many years ago, there are videos showing them working, and even then, though, even in their videos, if you watch closely, you will see fingers losing contact, you'll see the object slipping. And if you talk to people that program with these things, the usual, it's not hard to get them to start griping about how difficult it was. So it's a challenging thing to do. Now, so the question is, can you take an incredibly simple gripper and still get changes of grasp? And so that's what this graph is about. So we've got sort of different grasp types, our nodes in the graph, and then there are these behaviors that you would like to have. Now, the behaviors that are dashed are just ones we dreamt of doing, and the ones that are solid are the ones that we actually did. And so, and you can see there's some loops in here. So for example, you could throw the object up to the fingertips, and then you could drop it back to the palms, and you could do that over and over again. I'm going to show you a video, and this video is, this is a clip I took out. I just can't get this right, can I? So there's the gripper. It's just running that motor back and forth so you can see what the finger motions are. There's this triangular block. And you can see we're using this classification. So these are quasi-static. There's no dynamics going on there. And we're using external contact. This is called passive dynamics. Why is rolling to the fingertip? OK, yeah. And then active dynamic ones, throwing and flipping. One thing I like about showing this video to this group is, so this was a collaboration with Alberto, Nikhil, also Robbie Palini, some people at ABB. Anybody else I should be mentioning? Mike Erdman, okay. I forgot. But the reason I like showing it here is because, there's like twin goals for any talk, right? Is number one, you want to brag about your own stuff, and number two, you want to pander to the audience. So I've got them both covered with one video. Also, it's great because any questions you have, just ask away. I can answer any question you've got. We'll just ask Nikhil, okay? How do these things work? Now, some people look at this and they say, well, you know what? It's not that interesting because it's all scripted. And we were cognizant of that. And, if you listen to the video, if you read the paper, we're open about that. Nonetheless, you get that complaint a lot. But I think that, we learned from it. This is the point, okay? We learned from this, and so I'm back to this, this extrinsic dexterity is the name of the video. Extrinsic dexterity is an example of the space-time Telerobot. I mean, this is the best one I ever did, that I was ever involved in. When I say did, I mean watched. And my apologies to Nikhil, okay? I never saw him taking a nap, although somebody promised to send me a picture of him napping so I could. Did you send it to me? I'm sorry, I didn't get time to get it in the talk. Anyway, so he does nap, it turns out. But the point is, that we can learn from this system. And I think that's happening. There are people in my lab that have gone on to ask the question of how could you plan these things autonomously? How can you generalize from one object to other objects? And there's a similar excellent work going on here, and including Nikhil's. What's the name for, you have a different name for, it's prehensile pushing, is that it? Yeah, one of those operations that we're doing, Nikhil's done some interesting work on since then, prehensile pushing. Okay, am I leaving anything out? Is this sufficiently fair? Because really, I mean, if I wanted to draw this more accurately, there were 3 people in there, in that wrapper. Okay, besides Nikhil pounding away at the keyboard, there was Alberto and me twisting his arms, okay? So. But that doesn't help with the story of this. So, okay, that's about all I have to say about that. I want to talk about Berkshire Grey, but I think it ties into everything that I've been talking about. That is the question of how do you learn about manipulation? Because in the old days, boy, I hate to hear those words coming out of my mouth. Well, when I was a kid, Building 26 wasn't what you see. Building 26 was a wooden barracks. You have no idea how lucky you are. There was a wooden barracks right here, but you all already know that, right? Yeah, anyway. Yeah, lost my train of thought. Manufacturing, okay? Sad to say, somehow, starting about 10 years ago, all of a sudden people in robotics research started saying, oh, manufacturing automation is a solved problem, or it's not interesting, or there's no uncertainty. And it's very unfortunate because manufacturing is still a really awesome problem domain to work on. How does this interaction work? So this is what they have in theory. I think the Technology Transition Office at MIT, is it still called the Industrial Liaison Office? So that is a great title. We used to call those offices Technology Transfer Office, which is kind of arrogant. It's like, yeah, we're going to transfer our technology to industry. My experience is that it works the other way around. This is the theory, right? This is what the people in the ILO, they probably still believe this, that ideas and technology are going to industry, and then industry should supply dollars to us. My experience is kind of the opposite. I steal ideas, and they give us technology, and then what do I give them? It's not nothing, but it's a lot less than our technology transition office believes. I'll say that. So I think we have an amazing opportunity when we work with them, and I've always been looking for and wondering, like, what's the next killer app of robotics, something that's going to be commercial, that's going to kind of feed this process. And I've been very skeptical of everything that comes up. So, you know, people say, oh, domestic service robots. And you look at all the visions, and all these visions are really stupid. Uh-oh, sorry. Again, I'm not sure who I'm insulting. Let me rephrase that. I just did not see them. I did not see them as plausible. I am an overly skeptical guy, I think. And I was wrong about that, okay? The Roomba actually was a huge success, and it's a domestic service robot. People like to put it down, but I think that's wrong-headed. It's a very successful foray into domestic service robots. Now, what's the next one? You know, it's like, okay, you're right about that one. What's the next one? Butlers, they're going to cook in our kitchen, all these things, you know, someday. And it's interesting to work on. I don't doubt that. I just don't think that we're going to have an industry there in the next 2 or 3 years, or even 5 or 10, probably. So I'm very skeptical about these things. Elder care, you know, it's a beautiful application domain. Whatever we can do there is awesome. Do I think that we're going to have a huge industry there in the next 5 to 10 years? Doing the, you know, throwing up the kind of problems I'm interested in, I guess, you know, I'm skeptical about that. The surgery, obviously, there's been a lot of penetration, okay? But it's not autonomous, right? It's telerobotic, mostly. Again, I do think you can learn a lot from it. Domestic service, I said, oh, I'm writing down my list, which you can't see. See, I had a cheat sheet. Okay, materials handling, okay? Maybe this is the next great driving application. And the reason I think that is it shares 2 characteristics with manufacturing. What you see in manufacturing is hundreds, thousands of engineers building robots that do stuff, okay? And it's the Spacetime Telerobot, right? They're taking the same systems that we have in the lab and programming them to do new stuff. And they're learning things, okay? And we can learn from that. You know, that's why I have the ideas flowing from them to us. And we did learn a lot about manufacturing and about robotics generally from looking at factory automation, and we still are. It's still going on. I think materials handling has that same characteristic. It's not as big yet, but it's going to be. And why is it so big? It's crazy when you start thinking about it. I mean, everything you have started somewhere else, right? Everything has to flow, and you know, and it gets packed, and then that gets packed. You know, a screw starts in a box, and then that box gets in a case, and then that case goes on a pallet, and then that pallet goes in a truck, and then maybe even that truck goes onto a flatbed railroad car, or maybe it goes on a ship, and you know, and then it gets, you unpack it, then you repack it, you sort it. You know, everything you see, it's not just traveled some distance, which is relatively uninteresting, but every time it's being unloaded and unpacked and repacked and sorted and everything, there are these handling operations, many of which are manual. And so it's a really, really huge industry. There's another thing, which is that, oops, that was just my fault. There's another thing about materials handling in common with manufacturing, which is that robots have significant penetration there. So, you know, if I wanted to see something deployed in elder care, right, we have to cross a threshold that we haven't really crossed yet. Okay, if I want to see something deployed in factory automation, I just need to help them a little bit because the hardware is already out there, you know, doing its thing. And they're desperate for things. And I think the same is true of materials handling. So, you know, that's my pitch for materials handling. This is my, this is the moment I was thinking about this, and I thought I realized that I can tell you exactly when I switched from being a skeptic about killer apps of robotics to being totally convinced. And it was when Tom Wagner, so he was the CTO at iRobot for a few years, and before that he was a DARPA program manager, and now he's the CEO of Berkshire Grey. And this was when I was the director of the Robotics Institute, and I was kind of desperately worried about what I would do next, and the timing was perfect. Tom Wagner shows up, and at 10 a.m., I'm this hardened skeptic that doesn't believe anything's going to have any impact outside of manufacturing. And then 2 hours later, I'm like, I'm all in, okay? And so he kind of just kicked me out of the ivory tower. And I guess this is a little bit blasphemous. This is me in the role of St. Peter on the road to Damascus. Let's see, sorry, I'm borrowing from Catholic teachings, which probably many of you are. And that's God. I've got Tom Wagner cast as God, thunderbolt. Anyway, this is Berkshire Grey. I'm going to show you a video. This is everything that you see here except for people. There's a couple of people. So this is our little fleet of robots, FlexBots they're called. They carry bins around. This is a shuttle that we also built that moves things back and forth and drops things into bins. It's a reciprocating shuttle. Most of the ones you see in industry go around these long loops. The reciprocating thing has some advantages that are associated with this specific problem. Here you can see boxes getting inducted, they call it, into the system. So it's really big, and we're selling these systems. It is a going concern. The heart of the system, sometimes we say, I'm never sure whether I believe this or not, but I've heard Wagner say it, so I'll repeat it. The heart of the system is picking, and I know some of you are sick of watching videos of robots picking stuff out of bins. Nonetheless, here's another one. You really need to be careful and view these things with a skeptical eye, right? Because, everybody's video that shows them picking out of a bin works, okay? You'll see an impressive variety of stuff, and their system will pick all of them out, okay? But nonetheless, I think one thing to note here is that we are using suction, but we're picking things that can't ordinarily be picked with suction. So that bath sponge, that gauzy thing there, or pick something where there's not a good seal, where there's like a huge seam in it. Okay, so we're doing a good job with that stuff. So my thesis is that, and I want to say one more thing about that. So I've said that logistics, materials handling is big, but let me point something out. So people, I think, look at what's been going on sort of in the research community with respect to materials handling, and they see a lot of bin picking. And the thing is that materials handling, right, I was talking about this before, right, there's this whole workflow. When Tom Wagner showed up at CMU, my opinion was that materials handling was kind of a solved problem because Kiva Systems, which is now part of Amazon Robotics, had done this cool system that would bring shelves of inventory to workers that would pick from those shelves into bins. And it's very cool. They have these huge warehouses full of these shelves moving around. And it's like, wow, that's a cool problem. They really nailed that one, didn't they? I guess I'll look somewhere else, right? But that's just one thin slice of the workflow, okay? What you have to ask yourselves is, wait a second, okay, so, well, first off, it's obvious. Humans are still doing the picking with that system, or at least they were then. As far as I know, they still are. But there's a lot more. How does this stuff get on the shelf? Okay, how does this stuff get off the trucks? It has to be unpacked from the trucks. It has to be inspected. You got all kinds of goofy stuff going on. If you search on Amazon Robotics, how do we handle your inventory, I think it is, you'll find a very nice video that shows all of the sort of inbound processing of the stuff coming off the trucks. And there's people everywhere, okay, doing all kinds of stuff. So that's the nature of materials handling. There's an enormous amount of work still left, and I think it's going to be a good problem for a long time for us. So anyway, that's all I have to say, except I wanted to have to mention acknowledgments. Back in the good old days of the AI lab, we used our usernames. That's Tomas Lozana Perez, Mark Rabert, John Hollerbach, Bertold Horn, and Jerry Sussman were my advisors at some point. There's a funny thing that happened. Check time, 52 minutes. Oh, I better hurry. Yeah, there's a lot of people here that did a lot of the work that I was talking about. So that's it for me. Thank you very much. The end.
Any questions?
What's better than the trivial suction?
What's better than?
You said that you're doing a good job with the suction.
Yeah.
But it's still the suction.
Yeah. You know, Wagner's biggest problem when he recruited me was I did not know how to keep my mouth shut. There's a joke in the company to say it's a battery of proprietary technologies. And somewhere on somebody's shelf there is a battery that's the mythical battery of proprietary technologies.
Questions? Non-suction related. Oh, there's a question in the back.
So what do you think is the connection between your work and the very early work on industrial engineering?
That's an interesting question. I don't know enough. A few years ago, I got interested in watching humans, and I was vaguely aware, and I started kind of poking around and found some work on what people call motion time studies. Yep. Are you talking about that?
Yes.
Yeah, it's a really fascinating thing. There are some interesting videos. So one thing that happened was that people would put lights on limbs, and they would, the guy's name was, is it Galbraith, is that right?
There are several different.
Frank and somebody, Galbraith, who people might know because there was a movie made about them called Cheaper by the Dozen, okay, which is a bizarre cultural tangent. But then, yeah, that's not really the most famous one. I've forgotten now. It's very interesting, and I know there is a connection. There are some people in robotics that have taken the systems of work movement methods. I forget what the names of these things are. I'm not the right guy to describe this, but I think it is very interesting. And in fact, I have a book sitting on my dining room table right now that's like the Bible of engineered work measurement, I think is the title of the book. And it's very interesting, and they were there before us, and you can look at their methods and you can ask, like, to what extent is their descriptions of human workers' motion related to robot programming? Right. That's all I know what to say about that. Are you interested? Are you doing something related to that?
Yeah.
Cool. Send me an email. I'd love to know more.
All right.
Isn't it? Somebody should ask me, what did I learn so far? Oh my God. Because I keep saying that you could learn a lot from there.
What have you learned so far?
Was that really your question?
Not really, but you can answer that if you want. Then I can ask my other question.
One thing that's interesting is that that's too long-winded. I don't know. What's your other question?
Okay. If we look at other fields, like let's say like locomotion, flying robots, etc., you see that there are canonical problems. Let's say flying through obstacles, flying through windshields, walking through flat terrain, walking through rough terrain. Do you think is there something similar in robot manipulation aside from bin picking?
Yeah, I mean, the blocks world was kind of that, right? I guess we got tired of the blocks world. Bin picking was kind of that, and I think people are kind of beginning to get sick of bin picking. What would be a good substitute? You know, Leslie Kelbling was reminding me today that, you know, she thinks the kitchens are interesting. I think kitchens are interesting too. I'd like to kind of narrow it down. I don't know, it's an interesting problem because when you start narrowing things down, you get into the realm where a dedicated group of engineers can do it in a couple of years without necessarily learning a lot. So it's really hard to kind of hit that middle ground of something that's going to sustain interest for a while. I don't know, you got an idea?
I don't know. For competition, Tomás Lozano Perez told me the other day there are none, so I mean, maybe you can.
He said what?
There are none, so maybe you can beat him. And
there are none? I don't know. I think controlling a grasp of an object is an interesting one. You know, that's why we worked on that. Changing the grasp. There's a lot of them. Manipulation is really, really big. You know, I mean, if you ask yourself, like, how do you define it and how big is it? It's like it seems to encompass just about everything. Yeah. Oh, sorry. Come back.
With your new perspective, how do you think academia can help industry better?
Oh, okay. Let's see, what can we do for them? I'll tell you what, one thing is, we're obsessed with grippers, with hands. We're obsessed with hands. Why is that? You know, we just like to build machines that look like us, right? So we're obsessed with these hands, and even if you're not so crazy that you're trying to build an anthropomorphic hand, you're still building something that's fairly like a hand, like, you know, fingers, you know, including me. If you go out in industry and look at what they're using, anthropomorphic hands are non-existent. Grippers even as complicated as the Barrett hand or the Penn hand are also, I think, as far as I know, non-existent. Even the industrial grippers that are pneumatically driven and just snap open and closed, even those are actually not as common as you think. Vacuum totally dominates. And after vacuum, there's other things, you know, that are more kind of specific to the task, magnets and things like that. So now you can look at that and say, well, but, you know, suction cups are boring. And I guess that's kind of what everybody has done. I actually, you know, one of my students, maybe I shouldn't be saying this because he's working hard on it right now. So I'll keep it vague, but I think actually looking at what you can do with suction cups is a great idea. One little thing, I'm sure there are many more.
I have another question.
Yeah.
And this is not my question.
Oh.
Because of the connection with Tomás Lozano, I told him that if he were to record himself in video asking a question, I would put it here. And the challenge was that he had to ask the question before seeing your talk. So he didn't record himself, but he sent me the question. And the question was, why didn't you solve it with deep reinforcement learning? And I'm going to hold you to an answer.
First off, I don't really know how to do deep reinforcement learning. I have actually been working in learning for a long time, but my students actually do all the work, and many of them do know how to do that. So that's not the answer. Why not do it all with deep reinforcement learning?
You can remove the deep and the reinforcement if you want.
I mean, to some extent. So for instance, that gripper, that simple gripper that we built, that was designed to support machine learning. The initial design of that was such that if it grasps an irregular shape, the number of stable poses would be, subject to certain assumptions, a small finite number. And then, so then if you could train with an object for a little while, you could learn the algorithm that would map from the finger encoder values to the object pose. So the idea was machine learning of haptic. I'm telling you, you actually did this, right? You're the one that did it, yeah. Sorry, did I describe that correctly? You know, so I don't know. I'm a believer in learning. I'm not a believer that learning is everything. I think it's probably not. I also don't worry about it a lot. So, you know, there are some people that think that, oh, this is all going to be, you're going to be overwhelmed by machine learning. You don't need models. We'll just learn everything. And I mean, first off, that doesn't address the question of how do we learn about manipulation, except that it could help, right? So that would be nice. Don't worry about being made obsolete. I don't know why not. I think there's another question, another way of looking at it, which is that people who worry about this, I wonder why more people don't worry about it. I mean, why do the people that are doing algorithms for, I don't know, what are algorithms? What are they doing now? Let's say you're developing a proof system for Python certification, program certification, or something like that. Are you worried about being overwhelmed by machine learning? Is everybody worried about this? I think the reason roboticists are worried about it is because robots moving looks so cool that the machine learning people pick robotics as a good demonstration medium because they'll get a lot of views and a lot of interest. And so, you know, it's a good thing that we attract all that interest, but it could also cause anxiety, I suppose. I don't know. What was the question again? Why did I not? I don't know. Because I guess I think that it never occurred to me that that was the way to learn about manipulation, except maybe that one time it did.
Any other questions?
Question is, do you think the first truly generally useful robot in a home will have a suction cup or no? Or do you think it's mostly a like in the warehouse, suck the thing, drop the thing type of a thing?
You said that was an easy question?
Yes.
You think yes?
Well, so first off, if you look in your kitchen, what do you find, okay? I will bet you have at least 100, maybe 1,000 tools in your kitchen, okay? So when we talk about a human that's doing manipulation, you know, we think about the hands, and we think about how amazing the hand is, okay? Well, it is amazing. I'm not arguing against that. But in an applications context, okay, you are going to have an amazing assortment of tools, right? Now, the thing that the hands are, you can look at the hand as being great for two reasons. One is that it is, even naked, very capable. But not so capable that you don't need 1,000 tools in your kitchen, right? So, you know, it has its limitations in scope too. The other thing about it is that it's really, really good at changing tools, okay? And so we didn't go down this path, but you know, I have some video of Julia Child cooking, and one thing you notice is that her knife is flipping back and forth from the use it position to the stow it position in a fraction of a second, very, very quickly, okay? And you know, when you're getting ready to do a job, right, you're going to set things out in such a way that you can switch tools very, very quickly. So now, what does this have to do with the question about suction cups? I have a suction cup in my kitchen now, so my answer to your question was easy. Depending on how you define a robot, a human is a robot, and so I'm a robot, and I do have a suction cup in my kitchen, so, you know, question answered. I think the more interesting question is this. With robots, you want something that's going to change tools a lot. People who are into anthropomorphic systems, humanoids, and hands and so forth, they like to say, well, we don't want to have a whole new set of tools for our robots, so our robots are going to have to use our tools, and therefore they're going to have our hands, okay? I don't know that I believe that. I think when the time comes, you will say, no, I'm willing for my robot to have its own spatula that it can interface with more effectively. And what's more, my robot could have a spatula that interfaces not just mechanically, but with power and signal. And so my robot actually can have better tools than I have. And it can also have, well, anyway, so I'm kind of, you know, here's your question, you know.
Okay, I think that we should continue the discussion outside with food and drinks.
Yes. Thanks.